Hi, everyone, and welcome to this episode. Today, we're going to be solving some problems related to weak bases and their equilibria. If you spend enough time in the chem lab or if you're in a unit on acid-base equilibria, you're going to run into these types of problems. And I want to cover three main types of problems so that you have a plan of attack when you start seeing them. So they take a couple of steps. So grab a calculator and let's get it. All right, so let's start with a general setup so that you can kind of see how it might be different from a weak acid setup. So weak bases, they're bases because they accept protons according to the Bronsted-Lowry definition. And so a base, general B, some molecule, will go into the water and it will accept a proton from the water, not 100% of the time, but we're talking weak bases here, so some of the time. And because the water gives away one of its protons, we end up with an OH ion or a hydroxide ion in the solution, which of course raises the pH, makes it basic, and so on. And because weak bases set up equilibria, we end up with a equilibrium constant expression, sort of similar to the Ka expression, but slightly different. It's now we call it a Kb, and we have the conjugate acid of the base on top, and the OH ion concentration on the top, and whatever the concentration of the original base molecule is at equilibrium on the bottom. So make a note of this. We'll be using this equilibrium constant expression quite a lot today. And yeah, so let's go see how we're going to do it. All right, there are three types of problems that I need to cover today that you're likely to find if you're working your way through weak bases. And they include finding the pH from the Kb. So maybe you know what the base is and the Kb value, but you're trying to predict the pH. Finding the percent ionization from that Kb value, we'll take it a step further. And then flipping it around and saying, okay, well, if I know the pH, can I find the Kb value for this weak base? And yes, we can. So we're gonna go through all four of those. If you know which one you're looking for and you want to skip ahead, you can do that. Otherwise, just hang out and we'll solve some problems. All right, let's start with a very common weak base, and that would be ammonia. Example one here is ammonia. And the typical problem would be calculate the pH of a certain molarity of ammonia. And the Kb value for ammonia is 1.8 times 10 to the minus fifth. So what you want to do, always a good idea to write down the reaction that's going to occur and the Kb expression that we're going to use so that anybody reading your work knows exactly that you know, that they know, that you know, that they know what's going on. So enjoy that. All right, so let's say, okay, we put ammonia in the water in solution. And because it's a weak base, it's going to accept a proton from the water. So let's put the water here. And it's going to end up being NH4 with a plus charge. And some OH minus will be formed in the solution. So that's a general, that's our equation for this one, following the general rule on the other slide. All right. Because it's an equilibrium, I'm going to have to put an ice table down. And my Kb expression, let's just write it, is concentration of NH4 plus times the concentration of OH minus over the concentration of NH3 at equilibrium. Okay, so we're going to be filling in this little chart. The initial concentration is 0.01 moles per liter. And we'll say 0. And we're going to say approximately 0 for the OH. There is 1 times 10 to the minus 7th moles per liter OH in pure water. We're going to kind of blow past that, and it's going to become insignificant. But for right now, it's essentially 0. And we know it's going to go to the right. So 0.010 minus x, x, and x. All right. And at this point now I have to solve for x because my long-term plan here is to solve for x, which is the OH concentration, and then we're going to use that to find the pH. So we have 1.8 times 10 to the minus fifth is going to be equal to x times x, or x squared, over 0.010 minus x. All right, I'm going to go ahead and make the assumption. We're right on the border of being able to make this assumption. We got 3 factors of 10 difference here. So I'm just going to make the assumption that we're going to ignore that little x value that's there. It's going to be kind of more insignificant compared to this larger concentration. All right, so I get an x value of 4.24 times 10 to the minus fourth moles per liter. All right, that's my x value. Resist the temptation to just solve for x and race off to the next problem, because we actually haven't solved and answered our official question here, which is, what is the pH? Okay, now this concentration, though, is going to be, I'm just going to move up here, 4.24 times 10 to the minus fourth moles per liter. That's the concentration of the OH minus ion. Okay, and what I can do with that, I have to take two steps here to get the pH. I'm actually going to find the pOH. The pOH, which is the negative log of 4.24 times 10 to the minus fourth. And the pOH here is going to be 3.37. Okay, and that's great and all. We're one step away from getting the pH. If we know that the pH plus the pOH must equal 14, we're just going to find the pH, we're going to take 14 minus the pOH, and the pH now is going to be 10.62. And that would be my final answer. Okay, so a couple of steps. Ice table, equilibrium expression, solve for x. That's going to give you your OH minus concentration. And then take the negative log of that to get the pOH, and then subtract from 14 to get the pH. And guess what? Now it is your turn to try one of these. And I have a second example, and this is hydrazine. And so hydrazine has two nitrogens and a couple of hydrogens on the end. We kind of sometimes write it like this to show its structure. But along the way, it's going to gain an extra hydrogen from the water, producing the OH. Take a moment and see if you can find the pH of this solution. All right, and we're back. And so when I did this problem, I got a pH of 11.39. Doing the same procedure, my initial amount was a little bit higher, 2.0 moles per liter. And did the same type of expression, solved for x. X happened to be 2.45 times 10 to the minus third. And I included the concentrations of everything at equilibrium. Sometimes your problems will ask you for that. So you got to take the time to just write it out and say, I know what this concentration is, etc. And the pOH was the negative log of the x value, which was 2.61. And then subtracting from 14, I got 11.39. So if you got that, then great, good job. We are well on our way. Now, in a previous video on weak acid equilibrium, we talked about percent ionization, which is a way of representing what percent have actually done the reaction. And it's basically, let me write the formula again. Percent ionization equals the amount ionized, and very often that's pretty much your x value, over the original amount, and we multiply that by 100 to get the percentage. So we're going to actually use the problems we just did, just so we don't have to repeat everything. And so if you need to go back to see that other video, go ahead and do that. We use the percent ionization for weak acids as well. And so I went ahead, just to save some time, and to find the percent ionization of the ammonia in example 1, I needed the concentration of the OH, which is our x value, over the NH3 original. And our x value was this, our original was that, and it turns out to be 4.24% ionized for the ammonia in example 1. And since you were extra awesome and did example 2 with the hydrazine, let's take a moment and maybe you can try this, finding the percent ionization for your hydrazine example in example 2. Take a moment, pause the video, see if you can get it, and meet you back here in a second. Okay, when I did it, I got a small percent ionization because we had a larger amount at the beginning. 2 moles per liter makes it a lot smaller. OH over the hydrazine original, and I got 0.123% ionized on that one. So good job if you got that one. And let's go on to our third type of problem. And that problem is going to be something like this. The pH of a 1.0 times 10 to the minus third molar solution of pyrrolidine. I included a fun little drawing because pyrrolidine looks like this, and it would have a lone pair sitting on that nitrogen, just waiting for another hydrogen or a proton to be attracted to it. But this time we know the pH of the solution. Let's calculate the Kb for that pyrrolidine. This is one of the ways you can find the Kb for different things, is to dissolve a known amount of it, check the pH, and then work your way through this type of calculation. Okay, so let's get into it. I always want to write the chemical reaction. So pyrrolidine is kind of a complex molecule, so I'm just for the sake of keeping things simple, I'm just going to abbreviate PYR for pyrrolidine. And we're going to add some water to it. It's going to act like a base and accept the hydrogen or the proton from the water and produce an OH. Okay, and so that's our reaction. And it's going to be a similar process to before. We're going to do an ice table with our initial volume or molarity 1.0 times 10 to the minus third, 0 and approximately 0 for the OH. It's going to go down by x, and up by x. 1.0 times 10 to the minus 3 minus x, and we fill out our ice table. Hopefully by now you're kind of just doing these practically without thinking the ice tables parts anyway. Okay, so if I'm going to find Kb, then what I need to do is I need to plug in, that's actually H peer plus. Always include the charges when you're doing your equilibrium constant expressions. It'll make your grader very happy knowing that you know that what the charges are that they have. And you should write their charges because they have charges, and we need to honor the truth that they actually have charges and honor their journey in life. Okay, so this is going to be x squared over 1.0 times 10 to the minus third minus x. Okay, but here's the problem. So I'm trying to find Kb, so I need to know what x is. And I don't know what x is because I don't know what the Kb is. The clue here is that the pH is 10.82. So you kind of have to get to this point and go off to the side again and work with those pH values. So if the pH is 10.82, right, then the pOH is going to be 14 minus that. And so the pOH is going to be 3.18. Okay, so once we have the pOH, we can use that to find the OH concentration, which is X, and that gets us where we need to go. Rearranging the pH as the negative log equation, the OH minus is going to be equal to 10 raised to the negative 3.18. And that's going to be equal to 6.61 times 10 to the minus 4 moles per liter. Okay, so you kind of have to go off to the side and get what you need. And then we're going to bring it back in and plug it in for the x. So we're going to do 6.61 times 10 to the minus fourth moles per liter squared over 1.0 times 10 to the minus third minus 6.61 times 10 to the minus fourth. And when I punch that all through the calculator, I get 1.29 times 10 to the minus third as my Kb value. So yeah, and hopefully you're able to follow that along. So I'm going to pause the video in just a second for you to try one for yourself. Again, write the equation, fill in your ice table, set it up so your grader knows what you're doing, and then you're going to have to go off to the side to find out what x is using the pH equations, and then plug it back in. So if you are ready, let's try one more. And for this one, I picked a molecule called codeine. You may have had codeine before. It's a strong pain reliever, and all of that. I'm not advocating for its use, but it is used in a lot of cases. So there's codeine. Again, it's got a nitrogen with a little lone pair on there, waiting for a proton to come off of water. Take a moment, pause the video, and see if you can solve this one. All right, and we're back. And I will show you my solution for this problem. And I got a Kb value of 1 times 10 to the minus fourth, following the same procedure as I did in the other example. And again, an ice table, equilibrium constant expression, went off to the side to find what the OH concentration is, and then I plugged it in, squared it, subtracted it from the original, and I got 1.0 times 10 to the minus fourth. So if you got that, great. We accomplished what we needed to accomplish in this video. If you have any questions, please send them to me in the comments or directly. And in the meantime, happy solving and have a great day.